machine learning-based classifier to detect attacks in RPL-based IoT networks. Introduction to RPL. RPL stands for Routing Protocol for Low-Power and Lossy Networks. Purpose. It's specifically designed for IPv6-based routing in low-power and lossy networks. These are networks where devices have limited power, memory, and processing resources, like in IoT applications. Key concept. RPL builds a directed acyclic graph, rooted at a central node known as the sink or root. Goal. The protocol aims to minimize the cost of reaching the sink from any node. The path selection is based on something called an objective function, which seeks to find the route with the best link quality. Important terminology. DODAG, directed acyclic graph, a graph with one-way connections and no cycles. DODAG root, the central node with no outgoing edges, the top of the hierarchy. DODAG ID, a unique IPv6 address assigned to each node. Rank, a value that represents a node's relative position in the DODAG. Implementation note. RPL is implemented in NetSim based on RFC 6550, the standard that defines the protocol. Objective function and link quality in RPL. The objective function in RPL plays a crucial role. It determines how routes are selected and prioritized. In NetSim, RPL's implementation uses an objective function that prioritizes routes with the best link quality. So, better links mean better paths in the network. But what is link quality, and how is it calculated? Link quality in NetSim is influenced by two main factors: the received power of the signal, the receiver sensitivity of the nodes. To evaluate a link, NetSim calculates the quality in both directions, from sender to receiver and vice versa. The formula is link quality equals 1 minus the received power divided by the receiver sensitivity, where P is the received power in dBm. RS is the receiver sensitivity in dBm. These calculations give us two values. Transmit link quality for the forward direction. Receive link quality for the reverse direction. Finally, the overall link quality is computed as the average of these two. Link quality equals the sum of transmit link quality and receive link quality divided by 2. This final value is what the objective function uses to choose the most reliable path towards the root. In RPL, rank is a scalar value that represents a node's position within the DODAG. Its primary purposes are to measure the distance from the root node and help prevent loops. The root node, often the border router in IoT networks, always starts with a rank of 1. Ranks are computed using an objective function, as defined in the RPL protocol. The formula for rank increase is rank increase equals max increment minus min increment times 1 minus link quality squared plus min increment. Once the rank increase is calculated, the final rank of a node is determined as rank equals rank increase plus rank of parent, where max increment is 16, min increment is 1, as per RFC 6550. LQ is the link quality. This dynamic approach ensures that nodes farther from the root or with poor link quality will have higher ranks, maintaining a stable and loop-free topology. Example calculation for better understanding. Network type. IoT using the RPL protocol. Parameters configured in the given scenario. Path loss model. Log distance. Path loss exponent. 3. Transmit power. 1 milliwatt. Receiver sensitivity. Minus 85 dB. Reference distance. 8 meters. Rank of root node. 1. Parent of S2. Root node. To calculate the received power at node S2, we use the log distance path loss model. The formula is received power in dBm equals transmit power plus transmitter gain plus receiver gain plus 20 times the base 10 logarithm of wavelength divided by 4 pi times the reference distance plus 10 times the path loss exponent multiplied by the base 10 logarithm of reference distance divided by the actual distance between the nodes. Now let's plug in the values. The transmit power is 1 milliwatt, which we assume to be 1 dBm. Both the transmitter and receiver gains are 0. The wavelength is 0.125 meters, calculated using the speed of light divided by the frequency, where the frequency is 2.4 gigahertz. The reference distance is 8 meters. The actual distance between node S2 and the root node is 49.08 meters. The path loss exponent is 3. Adding everything, the received power is approximately minus 80.74 dBm. Now, we calculate the link quality. We use the formula. Link quality equals 1 minus the received power divided by the receiver sensitivity. Here, the received power is minus 80.74 dBm and the receiver sensitivity is minus 85 dBm. So we divide minus 80.74 by minus 85, which gives about 0.949. Subtract this from 1, and the final one-way link quality is 0.051. Let's begin by calculating the overall link quality between the root node and node S2. We take the average of the transmit and receive link quality. Both the transmit and receive link qualities are 0.051. So, the final link quality is 0.051. Now, we compute the rank increase using this link quality. The formula is rank increase equals the floor of the difference between the maximum and minimum increment, multiplied by the square of 1 minus the link quality, plus the minimum increment. In this example, link quality is 0.051. The maximum increment is 16. The minimum increment is 1. Substitute these into the formula. Taking the floor of this value, we get 14. Now, we compute the final rank of S2. We add this rank increase to the rank of the parent node, which is the root. The root has a rank of 1. So, rank equals 14 plus 1, which is 15. Similarly, after calculating the rank value for S1, the value obtained is 12. Now, since the parent of S1 is S2, and S2 has a rank of 15, we add that to our rank increase. 12 plus 15 gives us a final rank of 27 for S1. Similarly, the ranks for other nodes can be calculated. These ranks can be visualized directly within the NetSim DODAG visualizer. According to the simulation, the rank of S4 is 15, the rank of S3 is 28, and the rank of S5 is 27. Rank attack in RPL using NetSim. This is the topic we'll explore, examining how rank attacks affect. Let's begin by understanding how RPL normally works. When a network is being formed, the sender starts by broadcasting DIO messages. These are control packets that help nodes build the network hierarchy, known as the DODAG. Nodes that receive this message update their internal tables, choosing a preferred parent, identifying siblings, and recalculating their rank. Finally, the receiver sends a DAO message. This one carries routing information back up to the root, helping the network stay connected and informed. But what happens during a rank attack? A malicious node joins the network and listens to DIO messages, just like any normal node. However, instead of updating its rank honestly, it advertises a fake, much lower rank. Nearby nodes are misled by this information. They believe the malicious node offers a better route and update their own ranks accordingly, selecting it as their preferred parent. Here's where the real damage begins. The malicious node starts dropping packets instead of forwarding them. And because multiple nodes depend on it, this leads to a total breakdown in communication. The result? Zero network throughput and a compromised RPL topology. Consider the following scenario in NetSim. At the top of the network is the root node, also known as the 6-low-pan gateway. It begins the DODAG formation process by broadcasting DIO messages. Sensor 5 and Sensor 7, both within range, receive these messages and recognize the root as their parent. They respond by sending DAO messages, propagating route information upward. Sensor 5, behaving correctly, updates its rank and begins broadcasting DIO messages to its neighbors. But Sensor 7 is malicious. While it also updates its rank, it intentionally advertises a fake, lower rank to deceive nearby nodes. Soon, Sensor 6 and Sensor 4 receive DIO messages from both Sensor 5 and Sensor 7. Seeing the falsely low rank from Sensor 7, they select it as their preferred parent. They send DAO messages and route their data packets through Sensor 7. But instead of forwarding these packets, Sensor 7 drops them, silently sabotaging the communication flow. The impact of the rank attack can be clearly observed in the results window. The network throughput is 0, indicating that no data successfully reached the destination. By examining the packet trace, we see that after Sensor 7 receives data packets from Sensor 6 and Sensor 4, it never forwards them. This confirms the malicious behavior. The packets are being silently dropped. To further analyze the attack, users can visualize the DODAG using Python or MATLAB utilities. In the generated DODAG graph, it's evident that both Sensor 6 and Sensor 4 have selected Sensor 7 as their parent, solely based on its advertised lower rank. This visualization reinforces how the malicious node disrupted the network by misguiding neighboring sensors and intercepting their traffic. To build a reliable machine learning model for detecting attacks in RPL networks, we began by generating training data across multiple scenarios. We created 8 distinct scenarios, each with a different number of nodes, ranging from 6 to 39. In each scenario, we varied the number of malicious nodes, using values like 2, 4, 5, 6, 8, 10, 12, and 14. To ensure robustness, we ran each scenario 3 times using different random seeds. Packet tracing was enabled across all simulations, so we could closely monitor network behavior. This scenario used an IoT topology based on the RPL protocol, with simulated attacks from 2 malicious nodes. A Python script was used to process the packet trace and extract critical communication features from each sensor. These features include DAO messages sent, DAO messages received, DIO messages sent, DIO messages received, and the number of data packets received. This rich feature set helps the model learn the normal and abnormal behavior patterns of nodes under different attack intensities. Once the packet trace was generated, the next step was to process and visualize the data. We used a Python script to extract the relevant data from the packet trace to Excel file. In total, we gathered information from 534 sensors, and for each sensor, we extracted that 5 key features. To prepare this data for training, we performed feature normalization. This involved 2 simple steps. First, we calculated the maximum value for each feature across all sensors. Then, we divided each sensor's feature value by that maximum to scale everything between 0 and 1. After normalization, we moved on to manual labeling. Using logic within the Python script, we labeled each sensor as 1 for a non-malicious node and 0 for a malicious node. This labeled and normalized dataset now serves as the foundation for training our machine learning model. To better understand how each feature behaves, we performed feature visualization. Here are sample plots generated for a scenario that includes 2 malicious nodes. This scenario was simulated 3 times, each with a different random seed, to ensure variability in the results. The plots illustrate the normalized values of the extracted features, such as DAO and DIO messages sent and received, along with data packets received for each sensor in the network. These visualizations help us identify patterns and distinguish malicious nodes from normal ones based on their behavior. Feature visualization is performed for all scenarios. Once the features were extracted and labeled, the next step was to train machine learning models to detect malicious nodes. We used the process dataset to train the following 4 classifiers. K-nearest neighbor, which classifies a node based on the majority class among its closest neighbors. Radius neighbor, similar to KNN but considers all neighbors within a certain distance or radius. Support vector machine, which attempts to find the optimal boundary that separates malicious and non-malicious nodes. And logistic regression, a statistical model that estimates the probability of a node being malicious based on its features. Each model was trained on a portion of the dataset and then tested on unseen data to evaluate its performance in identifying attacks. After training the classifiers, we moved on to the inference using newly generated test scenarios. We created 6 new scenarios, each with a different number of nodes, ranging from 9 to 42. In these setups, the number of malicious nodes varied, specifically 3, 7, 9, 11, 13, and 15 malicious nodes were introduced to test the model's performance under diverse conditions. As before, Each scenario was simulated 3 times using different random seeds to add variability and realism to the results. This scenario used an IoT topology based on the RPL protocol, with simulated attacks from 3 malicious nodes. Features were extracted as before, but without manual labels. Classifiers then predicted malicious nodes in real time, just like in real-world use. The confusion matrix is a fundamental tool used to evaluate the performance of a machine learning model on test data. It shows how well the model is classifying by summarizing both accurate and inaccurate predictions. The matrix is especially important for classification problems, where we aim to distinguish between 2 or more classes. Let's break down the components of the confusion matrix. True positive. This is when the model correctly identifies a positive case. For example, recognizing a normal node as non-malicious. True negative. The model correctly identifies a negative case, such as detecting malicious node as malicious. False positive. The model misses a malicious node and labels it as normal. False negative. The model wrongly flags a normal node as malicious. From the confusion matrix, we derive key performance metrics. Accuracy tells us the percentage of correct predictions, both non-malicious and malicious, out of all predictions made. Precision measures how reliable the model is when it predicts a node as non-malicious, that is, how many of those predictions were actually correct. Recall evaluates the model's ability to detect all truly non-malicious nodes, ensuring it doesn't wrongly flag them as malicious. The F1 score provides a balance metric, combining both precision and recall to reflect overall performance, especially when there's a trade-off between false alarms and misdetections. Together, these metrics provide a comprehensive evaluation of model performance, helping us look beyond accuracy to understand how well the model handles both detection and false alarms. Confusion matrix and classifier performance. Let's now explore how these metrics play out using the support vector machine classifier for malicious node detection in an RPL-based IoT network. From the confusion matrix, we observe 324 true positives and 172 true negatives, only 2 false positives, and 0 false negatives. No normal nodes were mistakenly flagged as threats. From these values, we calculate an excellent accuracy of 99.6%, meaning the model correctly classified almost all nodes, whether malicious or non-malicious. Precision of 99.39%, indicating that nearly every node identified as non-malicious truly was, minimizing false alarms. Recall of 100%, showing the model correctly recognized all actual non-malicious nodes without mislabeling any as threats. F1 score of 99.69%, reflecting a strong balance between precision and recall, ensuring reliable identification with minimal mistakes. In the same way, we compute confusion matrices and performance metrics for the other classifiers, including logistic regression, radius neighbor, and k-nearest neighbor, each showing varying degrees of effectiveness in terms of accuracy, precision, and false alarm reduction. Final comparative overview and future direction. To wrap up, let's reflect on the performance of all 4 classifiers. All classifiers achieved 100% recall, meaning no non-malicious node was wrongly flagged as malicious. But precision varied, highlighting how each model handled the risk of missing actual threats by misclassifying them as safe. Among them, SVM led with the fewest false positives. It almost never misclassified a malicious node as safe. It consistently distinguished between normal and malicious behavior with minimal error, making it the most dependable model overall. Key takeaways. Perfect recall across all models, ensuring no normal node was incorrectly flagged. High precision, above 94%, meaning most nodes predicted as safe truly were, minimizing the risk of overlooking threats. F1 scores above 0.97 demonstrate a strong balance between detecting safe nodes and avoiding false assurances. As we move forward, future work will focus on testing against more complex and varied attack patterns, exploring additional attack vectors to improve detection across diverse threat scenarios, data classification and confusion matrix generation. Now, let's walk through how we classify the data, normalize it, and generate the confusion matrix. To begin, open NetSim workpage. Before we begin classification, it's important to note that both the training and testing samples must first be simulated and saved. Then select Open Workspace location from Workspace's icon. Then click on Python Files folder. Ensure all Python scripts, including the main script, are placed in the same directory. Before running the script, make sure to modify the directory paths inside main script to correctly point to your training samples and test samples folders. This step is essential for proper data access and processing. Once the paths are set, open the command prompt from the folder containing the scripts and run main script. This script will automatically process the packet trace files and generate a sensor message count CSV file inside each folder containing trace data. Once this is complete, the script will merge all the sensor-level data, normalize the features between 0 and 1 range, and create a combined dataset. It also prepares training data both with and without manual labeling for both the training and test samples. Now, using the manually labeled training data, different classifiers are trained, such as k-nearest neighbor, logistic regression, and support vector machine. Finally, predictions from these models are used to generate the confusion matrix, allowing us to evaluate each classifier in terms of accuracy, precision, recall, and F1 score. This process gives us a clear evaluation of how well each model detects malicious nodes in the network.